Hello, hydrofoil enthusiasts. My name is Mark Rice. I work for Maritime Applied Physics Corporation in Baltimore, Maryland. I'd like to talk to you about hydrofoil small waterplane area ships today, or HYSWAS. HYSWAS is a hybrid hull form, uses a combination of buoyant and dynamic lift. A good example of the buoyant lift would be swath. A good example of the dynamic lift would be a hydrofoil. In most HYSWAS concepts, the buoyant lift is larger than the dynamic lift. HYSWAS was conceived in the 1970s at the Naval Ship R&D Center in Carter Rock, Maryland. This was a period of high-speed ship innovation. Swath and hydrofoil vessels had been built by the U.S. Navy and were operating. Navy researchers were looking at hybrid hulls that could increase the payload and range while achieving excellent seakeeping capabilities, good fuel economy, and operating speeds approaching those of the hydrofoils. Like a hydrofoil or swath ship, a HYSWAS uses dynamically actuated submerged foils to provide the forces and moments that stabilize the vessel in a seaway. Like a hydrofoil, the upright stability of a HYSWAS at speed is dependent entirely on the flight control system that maintains the vehicle attitude. An engineer named John Meyer was the driving force behind HYSWAS development. John authored more than 50 technical papers and prepared a dozen concept designs. A free-running model was built and tested at Carter Rock to validate the control system relationships. Early HYSWAS concepts used thin struts similar to those on a hydrofoil, while later designs employed larger struts for access to engine and machinery spaces in the lower hull. John envisioned Navy and Coast Guard vessels in sizes from a few hundred tons up to ships of 5,000 tons. Many of these hulls optimized in a speed range from 35 to 40 knots, with favorable lift-to-drag ratios, good propulsive efficiency, and relatively large payload fraction. John Meyer secured $50,000 in small business innovation research funding in 1992 and solicited the design of a demonstration vessel. Our company of 4 people was fortunate to win this competitive contract and designed a 12-ton demonstration vessel that we named Quest in honor of John's tireless efforts. Using the Phase 1 design, John secured $750,000 for a Phase 2 contract. He then informed us that it would be possible to build the demonstration vessel for this amount of money. With the lofting and forming help of Bath Iron Works, a high-output diesel engine borrowed from Cummins Engine Company, and the skill of an aluminum welder named Steve Mantua, our company grew to 7 people and built the vessel in a Maryland warehouse. 18 months later, in 1994, we increased the overhead door opening in our rented building and rolled the vessel out on its cradle. The Quest was trucked to Annapolis, where it was crane launched in the Severn River. The lower hull diameter of 4 feet and the strut height of 4 feet were designed to allow operation in seas to 6 feet. The pilot house was equipped with 4 seats, each of which had a 5-point harness. The vessel had 2 larger forward foils and 2 smaller aft foils in an airplane configuration. Each of the foils was independently actuated. The 825 horsepower keel-cooled diesel engine was located in the lower hull with a hydraulic system. Removable hatches on the lower hull provided machinery access when the vessel was out of the water. The digital flight control computer superimposed the roll, pitch, and heave analog signals to the servo valves that controlled each foil. At low speeds, the broad hull provided roll and pitch stability required by the vessel's low center of buoyancy. When at low speeds, the vessel operates in a displacement mode with 12 tons of buoyant lift. 70% of the buoyant lift comes from the lower hull and strut, with the remaining 30% coming from the displacement of the upper hull. As the vessel accelerates through 15 knots, the lift on the foils unloads the upper hull, reducing its drag. At 20 knots, the upper hull is lifted free of the water surface, and the vessel rapidly accelerates to its 37-knot operating speed. Once foil-borne, the clearance between the upper hull and the water surface is normally between 2 and 3 feet. The submerged foils carry 30% of the vessel's weight by providing 3.6 tons of hydrodynamic lift. The forward foils carry approximately 3 tons of this lift with the aft foils carrying approximately 0.8 tons. At the design speed of 37 knots, the foil system is capable of generating 11.2 tons of lift before cavitation limits are exceeded. The resulting ratio of dynamic to static lift was slightly above 3. The difference between dynamic and static lift was used to maintain the vessel's roll and pitch stability in waves, and to drive the vessel vertically up and down to clear those wave crests that are higher than the strut. This action is called contouring the sea surface. Quest was equipped with a rudder on the trailing edge of the strut. Early testing indicated that the rudder deflections resulted in air being drawn from the surface, with a resulting deterioration in rudder performance. A fence was added above the rudder to minimize this rudder ventilation. The vessel is designed to perform flat turns, so the inboard and outboard edges of the upper hull remain the same distance above the waves. As the turn begins, the strut develops a lifting force that tends to roll the vessel away from the center of the turn. This force is counteracted by differential lift on the forward foils. Landing quest is quite simple. As the throttle is pulled back, the vessel settles onto its upper hull. Testing of the Quest moved to the mouth of the Chesapeake Bay for rough water testing. Initial testing compared the motions of Quest to those of an 11-meter rib when operating in 3-foot short-crested seas. The Quest demonstrated lower motions and the ability to sustain speed in a seaway. Our crew then took Quest on a series of trips offshore. The vessel demonstrated an ability to maintain 36 knots in 2-meter seas while contouring over the largest waves. The ride was comfortable, but visual effects were quite terrifying on a rider's first trip. In 2-meter seas, occupants saw 2-meter waves approaching at a relative speed of about 60 knots, while sitting about 2 meters above the ocean surface. Under these conditions, we were in awe of the control system's performance and the algorithms written by Dr. Don Higdon. We were able to take several defense officials on trips offshore. One such trip was interrupted by the breach of a humpback whale directly in front of Quest. A rapid splashdown avoided the whale collision. The testing of Quest led to interest in larger versions of the HYSWAS. MAPC was awarded a follow-on contract for the design of 850 and 2,200-ton vessels. A model of the 850-ton vessel was constructed and tested at the Naval Academy. This design utilized a single gas turbine in the lower hull to achieve top speeds above 40 knots. The Navy mine warfare community became interested in HYSWAS as a relatively small ship that could carry a helicopter. The 2,200-ton ship had the internal volume and the flight deck to handle emerging mine warfare systems, including a helicopter. Motions were predicted, including the effects of active motion control. In this animation, you can see the motion of the flaps on the main foils, with the vessel operating at 40 knots in sea state 6. To validate design predictions, we constructed a 20-foot model of the 2,200-ton hull and tested this at Carderock. The low-speed characteristics of the vessel were of particular interest since the lower hull and foils create high levels of motion damping when hull-borne. The model was equipped with block gauges to measure transverse loads at the junctions between the strut and the upper and lower hulls. Model testing was conducted over a wide range of speeds, sea conditions, and headings, operating in both the foil-borne and hull-borne modes. The damping of the lower hull provided low ship motions at low speeds, relative to other hull forms of similar size. The testing included low-speed operations in extreme seas. This video shows the vessel in sea state 8, where the significant wave height is 14 meters. This footage has been slowed down to represent the accelerations and motions that would occur at full scale. The Achilles heel of HYSWAS is its steep draft. The 2,200-ton vessel had a draft of nearly 11 meters, making it difficult to operate from small ports. When compared with a swath vessel of the same displacement, the draft of HYSWAS is 20 to 30% greater. While the HYSWAS hull has been on the sidelines for the last 25 years, there is renewed interest in its use as a yacht or passenger vessel in parts of the world where relatively large seas make voyages uncomfortable. The excellent seakeeping, high speed, and spacious upper hull are valuable attributes in these markets. With a renewed focus on green yachts, the ability to carry non-traditional fuels such as natural gas in remote lower hull compartments is of interest. For limited distance operations, the lower hull of a HYSWAS provides a location for a large battery bank that is isolated from any fire risks in habitable areas. With the use of a large counter-rotating propeller in the wake field of the lower hull, the propulsive efficiency can be very high. In other variants, a hybrid electric sailing vessel appears attractive. We look forward to seeing John Meyer's vision realized, and our congratulations to the International Hydrofoil Society on 50 years of great work. Thank you.